Hello, dear students. Today we have Proposition 36 of Book 3. If a point be taken outside a circle and two straight lines be dropped towards the circle, one of them touching it and one of them cutting it, then the rectangle contained by the two lines made up of the cutting line, that is to say, the whole of that line, and the line made up of the outside point all the way to the convex of the circumference, that rectangle will be equal to the square on the tangent. Pretty cool, huh? So here we go. We have two cases here. I'll talk about that in a second. But here's a circle and here's a circle. We've got, in both cases, one of them through the center, one of them not through the center. We've got a point outside, and we've got a straight line cutting the circle and a straight line falling upon the circle, making a tangent. Thus it is required to show in both of these cases that the rectangle contained by the whole of the straight line plus the line made up of the 2 points between the original point and the point on the convex of the circumference will be equal to the square on the tangent. That is to say, it is required to show that the rectangle contained by this and this will be equal to the square on this. Likewise over here, when it's not through the center, the rectangle contained by this and this line will be equal to the square on this line. I'm going to dash this one up too, just so we have our tangents all looking the same. Great. Let's start over here. Let's drop a line from the center to the point of contact of the tangent. Okay. Let's see. Well, we have, this case, we're going to rely on this proposition, book 2, prop 6 maybe, something like that. A straight line cut in half, and then a line added to it. We know that we've proven in this proposition that the rectangle contained by the whole straight line together with the added part and the added part plus the square on the half, remember this equals this because this original line was bisected, plus the square on the half, that was this case, will be equal to the square on the half and the added part taken together as one line. That is to say, this square. You should go look at that prop if you don't remember it to please your intellect, okay? So that's what we have here. We have a straight line, that's this original straight line. It's been cut in half. We know it's in half because this is the center. And a straight line added to it. I know we didn't do that, but you can treat it that way. And here you have a straight line cut in half, and then an added part. That's the way the intellect tells the imagination to think about it now. Great. Well, we know that, therefore, the rectangle contained by this and this plus the square on this will be equal to the square on this. Great. So, let's have some fun. The rectangle contained by this and this plus the square on this will equal the square on this. But look at this here. This is equal to this. So we can say if this equals to this, the square on this equals the square on this. But we had it earlier that the rectangle contained by this and this plus the square on this. Now we can say instead of the square on this, the square on this. Therefore, the rectangle contained by this and this plus the square on this is equal to the square on this. But this, the square on this, because this was a right angle. How do we know it's a right angle? Because this was dropped to the tangent, and we know from the center. We know if you drop a line from the center to the touching point of the tangent, it'll fall at right angles. So this is a right angle triangle. Therefore, the square on the hypotenuse is equal to the squares on the sides. But we already arrived at this conclusion so far. The rectangle contained by this and this plus the square on this is equal to the square on this. But the square on this, we can now say, is equal to the square on this and the square on this. Therefore, the rectangle contained by this and this plus the square on this is equal to the square on this and the square on this. Look, we have the square on this on both sides of the equation. Let's take equals from equals, therefore the remainders are equal. The rectangle contained by this and this is going to be equal, or is equal, to the square on this. But this is that line from the point, that original line that cuts the circle, and this is the tangent. So in this case, we've shown that if a point be taken outside a circle and a line dropped that cuts the circle and then touches the circle, when it passes to the center, it'll certainly be the case that the rectangle contained by the whole line and the line between the points of section of the original point and the convex of the circumference will be equal to the square on the tangent. Let's do the same thing over here. We have a point outside, a line cutting, a line touching. That's given. Let's have some fun here. We'll do different colors. We'll drop a line to the touching point, okay? And then we'll drop a line perpendicular to this. Therefore, we know it cuts it in half. A line from the center dropped it perpendicular to the line not to the center, cuts it in half. Great, and let's connect these 2 points. And for fun, we'll connect, we'll use black here. Just little itty bitty black points. Okay. All right, so here we have a line that's bisected right here at this green line. It's been bisected because this was dropped perpendicular from the center. Okay, we already showed that. Great. And let's do this part here, make this a long dash thing. Okay, so therefore we have a line cut in half and a line added to it. Therefore we know that the rectangle contained by the hole and the added straight line is one side, and the added straight line is the other side of the rectangle, plus the square on the half is going to be equal to, or is equal to, the square on the half plus the added part taken as one line. Great. So let's add this to both sides of the equation, sorry, the square on this to both sides of the equation. Therefore, we can now say that the rectangle contained by this and this, plus the square on this and the square on this, are equal to the square on this and the square on this. But the square on this and the square on this are equal to the square on this, because this is a right angle triangle, right? Okay, and the square on this and the square on this are equal to the square on this. Therefore, we can say that the rectangle contained by this and this plus the square on this is equal to the square on this. Let's add this to both sides. Therefore, we can say that the rectangle contained by this and this plus the square on this is equal to the square on this and the square on this. I did that wrong. Let's see. Where are we? Got this and this equals this, so this is the square on this will be equal to the square on this. Okay, we don't need to add that to both sides because it's already there. Okay, so sorry about that. So we were here. The rectangle contained by this and this plus the square on this is equal to the square on this. But this is equal to this, so therefore we can say that the rectangle contained by this and this plus the square on this is equal to the square on this. But the square on this is equal to the square on this and the square on this because this is a right angle triangle, because this has been dropped at right angles. Okay? So if the square on this will be equal to the square on this and the square on this. But the square on this was also equal to the rectangle contained by this and this plus the square on this. We've got the square on this on both sides of the equation. Let's sack it out. Therefore, the remainders are equal. That is to say, the square on this is going to be equal to the rectangle contained by this and this, which was what was set out to be proven. That if a point be taken outside a circle and a straight line drawn to be touching the circle and then cutting the circle, the rectangle contained by the whole line plus the line between the points of section of the point and the convex of the circumference will be equal to the square on the tangent. Quod erat demonstrandum. Thank you so much. Bye-bye.